Good morning. I am going to illustrate our study about the comparison of the performance of regional early warning algorithms in Europe that we performed in order to identify the best early warning algorithm to be used for the turnkey platform. In particular, I am going to introduce the study under two considered algorithms, the input data, the methodology adopted for the comparison, and the results obtained, to conclude with a brief overview on a companion theoretical study in which we focused on a particular aspect of the comparison. So, what is the purpose of an early warning system? The purpose is to deliver a rapid alert about an impending storm shaking, giving sufficient time for protective loss mitigating actions to be taken by targeted end users. Early warning systems are classified as regional, on-site, or hybrid. In the study, we specifically focused on regional systems, which are based on a dense sensor network located in the proximity of the earthquake source region. Regional early warning algorithms generally consist of different steps, which are the picking of seismic waveforms, the early detection of an event, the prompt evaluation of the location and magnitude, and eventually the estimation of the expected ground motion at the target site. The output of the early warning algorithms is then elaborated by a decision support system, which has the purpose to decide if an alarm should be issued or not. In this study, we consider two popular platforms for early warning widely adopted in Europe. PRESTo, which is a free and open source platform specifically developed for early warning, and SeisComP, which is instead a real-time earthquake monitoring platform made by several modules and that can be also used for early warning purposes. We decided to use SeisComP with the modules listed in this slide, which returned for simplicity VS in SeisComP, even if, strictly speaking, VS in SeisComP, which stands for Virtual Seismologist in SeisComP, is just the module for early magnitude evaluation that we used jointly with the commercial module scanloc for locating events. In both cases, PRESTo and VS in SeisComP, we computed the expected ground shaking through ground motion models. We compared the PRESTo and VS in SeisComP for European conditions of seismicity and network configurations, considering 27 moderate to large events from 5 turnkey testbeds. 14 events are real events occurred in Iceland, Francia, and Western Greece, for which we processed observed recordings, while the remaining 13 events are earthquake scenarios in southern Italy and the Pyrenees, for which we computed and processed broadband physics-based synthetic seismograms. We considered local velocity models from the literature for both the computation of synthetic seismograms and the early warning algorithms. Lastly, we computed the ground motion using the European GMP by Akkar et al. 2014 for shallow crustal events, and the GMP by Youngs et al. 1997 for the deep events of the Francia region. We ran playbacks of the seismic waveforms using both PRESTo and VS in SeisComP. We evaluated and compared the performance of both algorithms in terms of the source parameter estimates, magnitude and location, and the corresponding ground shaking predictions at selected target sites. In fact, the output of their algorithms are magnitude and location estimates that evolve in time. Therefore, they can be compared at each temporal instant to the real values provided by bulletins. In this plot, we can see the temporal evolution of the epicentral error, depth error, and magnitude error for two earthquakes. These timeline plots enable us to assess the timeliness of early warning. In other words, how quickly each algorithm can produce the first joint location magnitude estimate and the time necessary to achieve a stable source estimate. We define the stable time as the time at which the early warning estimates stop changing significantly in time. Moreover, these timeline plots allows us to assess the accuracy of the source parameters. In other words, how much magnitude and location deviate with respect to the corresponding bulletin values. In the first comparison was therefore performed in terms of timeliness at two temporal instants, the first instant and the stable instant. Our analysis revealed that the first early warning estimates are provided slightly faster by PRESTo. We also found that VS in SeisComP location estimates retrieved from scanloc converges to stable values faster than those of PRESTo. In contrast, VS in SeisComP magnitude estimates required a longer time to become stable. The second comparison aimed at evaluating the accuracy at the two selected instants. We found that the first estimate of epicentral distance and depth by VS in SeisComP are more accurate than those provided by PRESTo. The location performance of both algorithms is very similar at the stable instant, although the dispersion of the stable depth estimate error for PRESTo is almost double than that for VS in SeisComP. Concerning magnitude, PRESTo is more accurate at the first instant, while VS in SeisComP is more accurate at the stable instant. We also explored the effect of the location and magnitude estimates on the corresponding PDA prediction at the selected target sites, one for each considered testbed. At this purpose, we applied a ground motion model to the source parameters at each temporal instant, obtaining a ground motion that evolves in time. Again, we performed two types of analysis. The first examined the temporal evolution of PDA estimates by computing the number of trend inversions in the temporal evolution of PDA, which can raise questions about the integrity of an issued alarm if the PDA threshold for issuing an alarm is exceeded at a certain instance, but not exceeded at a later instant. Our analysis shows that the number of inversions for VS in SeisComP is lower on average and has a smaller standard deviation. VS in SeisComP has also a slightly greater number of cases with 0 inversions. Conversely, PRESTo has some cases with more than 10 trend inversions. Therefore, we concluded that the integrity of the ergocally warning alarm issued by the VS in SeisComP algorithm is higher than that for PRESTo. The second comparison aimed at estimating the ground shaking prediction accuracy, which was quantified using a specifically designed metric that measured the difference between the cumulative distribution function of PDA produced when the bulletin source parameters are used in the ground motion model and the cumulative distribution function obtained for a given algorithm's source parameter estimates at a prescribed temporal instance. The better the performance of an algorithm, the lower the value of the MBD metric. We consider 3 temporal instants corresponding at 3 different lead times at the target sites, in the specific 15 seconds, 10 seconds, and 5 seconds. It can be seen that the PRESTo provides more accurate ground motion estimates at the largest lead time considered, while VS in SeisComP produces more accurate ground shaking predictions than PRESTo for the smallest considered lead time. This trend reflects what was observed in case of magnitude accuracy. The analyses presented so far were performed neglecting the uncertainty on the source parameters, since VS in SeisComP did not provide the uncertainty on magnitude estimates. Therefore, we conducted a theoretical comparison of the PRESTo and Virtual Seismologist algorithm, explicitly considering the accuracy and the uncertainty of location and magnitude estimates. In this case, we consider the original Virtual Seismologist algorithm and we use MATLAB implementation of the algorithms in order to allow using exactly the same input data for both algorithms. We used almost the same data of the previous set of analyses. We examined the accuracy of source parameter estimates from both algorithms for different levels of uncertainties. We used 3 different levels for the coefficient of variation in case of location and 3 different levels of standard deviation in case of magnitude. We then translated these estimates into ground shaking prediction distributions using ground motion models, also propagating the uncertainty on the source parameter estimates. We measured the MD metric across each of the events of interest, and a summary of this is shown in this picture for one particular level of uncertainty of the source parameter estimates, which shows, in this case, comparable performance between PRESTo and Virtual Seismologist. However, we found out that the best performing algorithm in terms of ground shaking prediction depends on the uncertainties introduced by the underlying source measurements. To conclude, we concluded that PRESTo has a greater risk mitigation potential than BS in SeisComP in general. This is because PRESTo produces faster and more accurate early magnitude estimates, which result in better ground motion estimates for the long lead times. Predictions by BS in SeisComP are eventually more accurate than those by PRESTo, but the length of time this requires results in smaller warning times. Therefore, we suggested to use PRESTo as early warning algorithm for the turnkey platform. Alternatively, the PRESTo magnitude algorithm could be independently implemented within SeisComP as an additional module for early warning magnitude evaluation, in order to use it jointly with the scanloc module for locating events, which we found to be the best algorithm for location evaluation. It should be noted that the study outcomes should be interpreted as an average performance of the examined algorithms across different seismicity and network geometries in Europe. But a more detailed feasibility study is recommended for target or region-specific applications of the algorithms, possibly recalibrating the algorithms coefficients according to the study area. Finally, the results of the theoretical analysis focused on accuracy and uncertainty highlighted the importance of explicitly accounting for source parameters uncertainties when measuring the accuracy of final early warning predictions. If you are interested in the details, both studies were recently published as 2 companion papers, and the references are provided in this slide. Thank you for your attention.